Good morning. Today we are going to discuss the urinary system. And the urinary system has many functions, not just filtration of the blood and excretion of the unwanted substances or toxins, let's say, in the form of urine, or the reabsorption of the ions and other minerals that we need back into the blood. Therefore, it's not just the filtration that that the kidney is responsible for. It's responsible for many other functions that we'll discuss in a few minutes. So when it comes to the overview with the urinary system, an overview of it, it's a major part of the homeostasis by maintaining the composition of the blood, the pH and the volume of the body fluids within normal limits. And that in itself can tell you a few things. It tells you that it maintains the composition of the blood, which means those that you need to reabsorb back into the blood regarding the sodium, potassium, calcium, all the ions that you need, including other amino acids and other proteins that we need, small proteins. It controls the pH, and I'll discuss that in a few minutes too. It maintains the pH, and this will be a focus of my lectures for the coming few chapters. So I want you to pay attention, pay big time attention to this one. And of course, controlling body body fluids, and that has a lot to do with hypertension and blood volume. So just these are three main functions. The urinary system, like I said, removes metabolic wastes, substances that we have in excess, any foreign substances such as drugs and toxic metabolite. And this is a big one for drugs. Drugs are filtered through the body by two organs. They're filtered by the kidney and they're filtered by the liver. That's why sometimes if you are taking medicine, specific drugs for a while, for a long time, they actually do liver enzyme panel, liver test on you just to make sure that the drug is not doesn't have a negative impact on your liver. And also many have an effect on the kidney. Therefore, taking drugs should be something that we consider carefully, relying on knowing the fact that the byproduct of a drug breakdown will be filtered mostly through the kidney, but there are many through the liver. So just be careful about that. The urinary system consists of the following organs. Consists of the kidney, consists of the ureter, the urinary bladder, and the urethra. The kidney, as I said, is the filter system. The filters the blood, and then whatever is left over will be the urine. The ureter is the tube that transports the urine from the kidney to the urinary bladder. And the urinary bladder is where the urine is collected. And of course, eventually it will be excreted out through the urethra. So here we have the structure one more time. Here is the kidney, which is, again, the kidney is a bean-shaped kind of structure. Here is the ureter. This is the ureter, going through the urinary bladder, and out will be the urethra. Notice the blood vessels. Here is the inferior vena cava. That's the inferior vena cava. That takes blood away from the deoxygenated blood away from the lower organ systems back up to the heart. So the heart can pump it out to the lungs to get reoxygenated. And of course, here is the abdominal aorta, which supplies the renal artery with the oxygenated blood and the nutrients that the kidney would need in order for it to function. Now, that tells you if, God forbid, you have an aneurysm, which is bulging in the blood vessels, and we'll talk about that a little more when we talk about blood vessels. That bulging, if it ruptures, that's what aneurysm is, then that will compromise the blood supply. Actually, it should be down here. But either way, that should compromise the blood supply into the kidney, and that's why that can cause serious damage to your kidney and might end up on dialysis if it's not treated on time, or can actually be fatal. So that tells you that here we have the renal artery, renal vein, and those are connected directly. The renal artery connected directly to the aorta. The renal vein is connected directly to the inferior vena cava. So again, what we're talking about here is that the urinary system consists of kidneys, ureter, urinary bladder, and the urethra. The ureter connects the kidney to the urinary bladder, and the urethra connects the urinary bladder to the outside. Together, these organs make up the urinary system, and it has many functions. The first one, like I said, filtration of the blood. So filtration of the blood plasma. Let's be clear about that. Filtration of blood plasma and reabsorption of needed minerals, of let's say essential substances, things that you need to put back into the blood, and the secretion of excess ions or excess metabolite or drugs or toxins. Okay, so just keep that in mind. These are the three main functions. Now, like I said, the kidney does the major job of the urinary system. It filters gallons of fluid from the bloodstream on a daily basis. The other parts of the urinary system, the ureter, the bladder, the urethra, are just passageways. And in case of the bladder, not just a passageway, but it's actually a temporary storage for the urine. Now, after the kidney filters the blood, like I said, it retains most of the water and many of the solutes back into the bloodstream. And the remaining water and solutes will make up the urine. So what you reabsorb is what you need, and all the excess will eventually become the urine. And that urine will pass from the kidney through the ureter to the urinary bladder and out through the urethra. So this is a very complex system, especially when you begin to focus more on the kidneys. And therefore, I'm going to focus a little on the kidneys. But before I do that, I want to give you an overall picture of where we're going with this, because I just don't want you just to focus on filtration. There is more to the kidney than just filtration. So I'm going to go to the whiteboard and share my beautiful handwriting again with you. Let's see, share, whiteboard. So here we go. So in case of the in this case, you'll have the pH. Let's talk about pH to talk about the pH and show you the connection between pH and other systems, between the kidneys and other systems. And remember, if you recall from the endocrine system, you have many hormones that play a role in ion movement in and out of the blood, and how much you need to keep versus how much you need to excrete out. And if you recall, we spoke about a few of them. For example, we spoke about, we spoke about the aldosterone, that's one. And we spoke about, of course, the AMP from the heart. And I said the act antagonist, one keeps the sodium and one actually forces you to excrete the sodium. But either way, if you just look at the aldosterone alone, you'll notice that whenever the aldosterone is secreted from the adrenal cortex, what will happen is that it acts on the nephrons, which is the functional unit of the kidney, and the nephron will reabsorb back the sodium. So the sodium goes, let's say here's the blood, here is the nephron, and let's see, what is a different color. Here's the nephron in yellow, and what you'll have is that when aldosterone acts on the nephron, then sodium will flow back or will get reabsorbed back into the blood. And like I said, whenever the sodium flows back where the goes in one direction, the chloride ions will follow, if you recall. And that means now you have more salt on this within the plasma of the blood, and therefore the water would follow. If you recall that, the water would follow. And I said on the other direction, on the other direction, you'll have potassium leaving back excreted. You have hydrogen ions also being excreted out, hydrogen ion, H+. So this hydrogen ion, again, it directly influences pH, because the more hydrogen ions you have in a solution, the more acidic it will become, the less acidic. And if the hydrogen ions go in one direction, and I stated that in the previous lecture, then the bicarbonate ion will move into the blood, HCO3-. So this HCO3, the bicarbonate, that makes your blood alkaline. So that bicarbonate makes the blood a little alkaline. So you can see that just within the kidneys alone, you have, even though you're talking about reabsorption of sodium, but again, that reabsorption will cause water to flow toward where the sodium is going, and also excrete out the hydrogen ions. That hydrogen ion excretion has a direct effect on the actual pH. So that's the kidneys. Now, the kidneys, when it comes to the pH homeostasis, does not act alone. What you have on the other side that we'll discuss later on is the respiratory system. And even though I'm not discussing the respiratory system now, I do want you to keep in mind that it will directly connect back to the urinary system. And we'll talk about that later on too when we discuss the respiratory system. And this has to do with two cases, that's a conditions that are called acidosis and alkalosis. And this pretty much, these two conditions are affected directly by respiration. Now, the main one that controls pH of the blood, the main system that allows for the overall control, the big picture, let's say, control the pH, is the respiratory system. It's the respiratory system. And what I will do is just to give you a good overview really quick. So if you have the carbonic acid, H2CO3, this dissolves into or dissociate into the carbonate ion and the hydrogen ion. This carbonic acid actually comes directly from breathing, from respiration. So when you have CO2 plus water, this will give you that carbonic acid. This occurs in the red blood cells. In the red blood cells. So you have, anytime your system is transporting carbon dioxide back to the lungs, about 73% of it interacts with the water inside the red blood cells and becomes carbonic acid, and the rest of it actually binds to the hemoglobin. So by the time it gets to the lungs, it goes back to water and carbon dioxide, and then you exhale the carbon dioxide out. So again, what you see is that the carbonic acid mostly found in the red blood cells, and anytime the plasma, the buffer system declines or decreases in concentration, it diffuses out from the red blood cells back into the plasma to substitute for the loss of the carbonic acid. So again, the carbonic acid is the main buffer system that we have in our system. There are other two systems, but this is the main one. You see that the supply of the carbonic acid obviously comes from respiration, as you can see from red. So the carbon dioxide with water gives it the carbonic acid. This dissociates into the carbonate ion and the hydrogen ion. Now, the more hydrogen ions you release into the blood, the more acidic it will become. That's why if your plasma is acidic, you begin to hyperventilate, deep hyperventilation, to force this reaction to go backward, to reverse the reaction, going in this direction. And at the end, what you release is that carbon dioxide out. So those who are in nursing, or those who are practicing within the medical field, and you are involved with someone whose blood plasma is a little acidic, you'll notice there is they give them oxygen and allow for deep breathing to allow for that carbon dioxide excretion. Now, if exhalation. Now, if you have your blood is becoming a little alkaline, then obviously you hypoventilate, which means that the reaction will go forward, and now you release more hydrogen ions into the plasma, and that means you become more acidic. The blood becomes more acidic. Now, this is the overall picture of the respiratory system. The fine-tuning of it will be through the kidney. Meaning, so anytime you gets you up to the alkaline, but to be specific, let's say 7.3, 7.2, that fine-tuning with the buffer system occurs in the kidney. That's the kidney. The kidney fine-tunes the whole thing. So what I want you to remember before I go back to the kidneys is that whenever there's a problem with the respiratory system, so let's say the problem is here, you know, you're a heavy smoker, the kidney will compensate to maintain the pH. If there's a problem with the kidney, the respiratory system will compensate. Okay, just keep that in mind. We'll come back to it when we do the respiratory system. A problem with the respiratory system, the kidney or the urinary system will compensate. If there's a problem with the urinary system, the respiratory system is going to compensate. So let's keep that in mind because we will come back to this one, okay? We'll come back to this one when we do the respiratory system, and I just want to show the connection between these two. It's very important that you remember that. Now let's go back to the kidneys. Notice that if water goes in one direction, that affects the volume within the blood volume, which again affects blood pressure. So just keep that in mind. That's the relationship between aldosterone and blood pressure. And if that gets involved, you know, there are other hormones will act on the nephron, such as the ADH, the antidiuretic hormone, to allow to retain more water or to allow you to excrete. So the less ADH, the more water you excrete, the more ADH secretion, the more water you retain. And we keep that also in mind as we discuss the chapter. Now you see why I'm going from I started with the endocrine system, and then I'm moving straight to the kidneys, to the urinary system. And then after that, I'm discussing electrolytes, which is this, you know, sodium, potassium, chloride, and all that, chloride ions and all that. And once I finish that, I'm going straight to the respiratory system. Now you see that I'm following the story of homeostasis and pH and electrolytes. So that's the theme for this semester. Pay attention to this because that's what I'm focusing on big time. If you understand this and you understand the story behind all this, then you pretty much have mastered the main points or the main topics that you need to know from AMP2. Again, let's go back. I'm going to switch back to the PowerPoints again. Let's see, where is the PowerPoints? Where is the sharing? So now I'm going back to the kidneys. Let's make sure that I'm back on the kidneys. Yep, very good. We're back to the kidneys. So now, as you can see, that the kidney is that reddish brown bean-shaped organ with a smooth surface. In adults is about 12 centimeters long and 6 centimeters wide, about 3 centimeters thick. It is enclosed in a tough fibrous capsule. And the kidneys are they lie on either side of the vertebral column. So let's write that down. Let's see, where is it? They lie on, on either side of the vertebral column. They are between, you can say, the peritoneum and the back wall of the abdominal cavity. Between the peritoneum and the back wall of the abdominal cavity. It is, you can say, at the level of the 12th thoracic and the first 3 lumbar, so L1, L2, and L3. Let's see, the top portion, the superior portion of it, is protected by the 11th and 12th pairs of the rib cage. Let's see, just make sure I cover everything. The kidney is slightly lower on the left, so slightly lower on the left side. And the reason being is because the liver occupies most of that area, because of the liver. You can think of your kidney about the size of a bar of bath soap. And surrounding each kidney, let's see if I can go back. Surrounding each kidney, you have a smooth renal capsule, and I'll show you that in a minute. Let's go back actually to the actual one. Let's see. Surrounding each kidney, you have the renal capsule. You have connective tissue sheath that helps maintain the shape of the kidney and protect it against trauma. And you have the adipose tissue that pretty much maintains that, the adipose tissue that surrounds the renal capsule and gives it the cushioning that the kidney needs. It has also a thin layer of irregular connective tissue, and also just keep in mind that the adipose tissue anchors the kidney to the posterior abdominal wall. Anchors kidney to the posterior abdominal wall. And again, the major processes of the kidney is filtration, reabsorption, and secretion. So 3 things that we're going to talk about. You have filtration, reabsorption, and secretion. Again, just summary, let's go back just a little bit to summarize what's going on here with the kidney. I'm going to go back to my favorite whiteboard. Start a new page. And what you have is the main functions, and I'm going to talk about them really quick. The first one, now that you know most of the general overall structure of the kidney, the first function is I hate it when it stops writing, is regulation of blood volume and blood pressure, which means that the kidney would adjust the volume of the water in the blood by returning water back into the blood and or eliminating it in the urine. So depending on maintaining homeostasis of blood pressure. And this way, by either retaining water or letting go of water, will regulate blood pressure. Of course, we can keep in mind again. So if you have here's the blood vessels. When you add water to it, you're increasing blood pressure. When you let water out, you are decreasing the blood pressure. and that's a way of maintaining homeostasis. And again, that's aldosterone, for example. ADH can play a role in that. But there's another one that we're going to talk about. We're going to talk about the renin later on today that also plays a role. Renin, R-E-N-I-N, that plays a very important role in maintaining blood pressure homeostasis. So keep that in mind. The other system, the other function that we're going to talk about is regulation of blood composition, regulation of blood composition and pH, blood pH. Like I said, the kidney affects blood composition by regulating the blood levels of several ions, ions like sodium, potassium, like I showed you before, going in and out of the blood. And they also regulate the pH, again, by working with the ions, by working with hydrogen ions, which if you have more, that becomes acidic. And if you have more of the carbonate ion, then you're talking about ion becomes alkaline. So again, a higher concentration of hydrogen ions in the blood, you're talking about more acidic, whereas more carbonate ion, the blood becomes alkaline. So that's one more. Let's talk about two more major functions as well. So number 3, the main is production of 2 hormones. That's right. If you recall, I discussed from the endocrine system 2 hormones that the kidneys is responsible for, production of hormones. So hormones, again, are not just secreted by glands. There are tissue that secretes hormones as well. In this case, the kidney secretes 2 main hormones. The first one that we're going to talk about last time, but now I'm adding it, is called the calcitriol. The calcitriol, that's responsible for, or that's pretty much like you need it in order for you to absorb calcium into the blood from diet, and this pretty much is the active form of vitamin D. The active form of vitamin D. That's calcitriol, again, produced by the kidney. And another one that we spoke about is last time in the endocrine system, I said erythropoietin. And erythropoietin produced by the kidney, it travels to the bone marrow, and then the bone marrow will produce red blood cells. So again, the kidneys also have to do with production of red blood cells. Red blood cells are responsible for carrying carbon dioxide as a carbonic acid back to the lungs. So you're going to see a connection now between the actual kidney skeletal system, the bone marrow of the skeletal system, and the blood and homeostasis. So that's another connection between 3 different systems that we're talking about. I want you to begin to see the big picture, not just focus on one chapter. You can see there is more than one chapter that plays a role here, and you can see it clearly. For example, if I will ask a question about erythropoietin, and then I'm talking, then I am, one of the answers might be about red blood cells, or the answers will be about pH. Just be careful, because there is a connection between the 3. So it just depends on what the question asks, and these are the ones that you can, play tricky questions. So be careful with that, with those points. You can see that erythropoietin, you're talking about kidneys and pH. Then you can see that it has a lot to do with interacting with the skeletal system, with the bone marrow, producing red blood cells, which again affect the pH. So you can see the more than one route I can ask questions different ways. Just be careful. And the last function that we're going to talk about is the excretion of waste, which that's what we know about most of us know that about the kidneys. Excretion of waste. So, and that's pretty much the urine produced or formed at the end. So the kidneys will excrete all that waste, substances that are excess, there are no use of it. These waste can be from metabolic reactions in the body, So let's say if you're exercising or all the excess metabolites that you have are going to be excreted out. You have metabolic waste, for example, that include ammonia, urea, let's see, bilirubin. I will talk about that in the digestive system, which is a byproduct of bile acid metabolism breakdown, and that has a lot to do with jaundice. We'll talk about that when we get back to talk about the blood and the digestive system. Another one you waste is you release is creatinine and uric acid. And uric acid. It could be like I said, the byproducts of drugs. Keep that in mind, and could be. And that's, I'm sorry to write that down, but it's so unfortunate that it becomes a reality now. For those who don't believe environment is important. So here we go. When they have environmental toxins that can cause many disorders that we have, and thank God for the kidney that excrete most of it out. But too much exposure to environmental toxins eventually will lead to serious health problems. So for those who don't believe environmental toxins, there will probably a day that you will. All right, so now we are discussing we discussed the four main functions. This is just a very detailed chapter. Let's see what this on the side. Switch back to desktop. So we discussed most of the, we discussed most of that. Let's go to the next slide. So here's a good example of them. We make this figure a little better, larger for you. So what you can see here, you have the kidney. You see the adipose tissue that surrounds the kidney. Here is the renal fascia, the outer layer. Here is the parietal peritoneum. Again, here's the blood vessels, the vena cava. Here is the pancreas. We're going to ignore all that. Here is the aorta, the main blood supply to the organ system. Again, take a look at the picture in the bottom, the B. You'll see the kidneys again. Here is the renal fascia again. That pretty much composes the area of the kidney. Here is the adrenal gland at the very top. Remember, there's two of them on the top of each one, on top of each kidney. And of course, here is the parietal peritoneum. Remember, parietal is in touch with the outside. The visceral is always in touch with the kidney, and in between you have the fluid. If you remember that from chapter 4. These are more of epithelial tissue that makes up those layers that connect the kidney, or that cover the organs. Okay, these are called the serous membranes that cover them. Okay, we are done with that one. So if you take a look now at the actual kidney and see what is it made up of, it's made up of many different structures. You have the renal sinus, you have the hilum, you have the renal pelvis. The renal pelvis has two main parts, two main, major calyces and minor calyces. Plural is calyx, but since you have more than one, it's called calyces. You have the renal medulla, the cortex, the column, and the renal capsule. And of course, the nephron is the main functional unit of the kidney. So I'm going to take each one now and talk about it in a little more detail. So here's the kidney. I'm going to see if I can amplify this one for you, make it bigger. So in regards to the, let's start with one at a time. So you have the renal cortex. And you can see the renal cortex is this area here, from this point to this point. And here is the renal capsule, which covers the entire kidney, all around the kidney. That's the renal capsule. All right, so the renal capsule is that connective tissue and that connective tissue sheath that maintains the kidney shape and protects it. So that's the one that we first started in the previous slide. So it connects it kind of protects the kidney and keeps the correct shape for it. And then you have the renal cortex, that's the underlining layer, and this is like red outer region of it. Okay, and if you go back, so the renal cortex is the outer region of the kidney. And this will be followed by the renal medulla, which is the second part. It's again the third layer, which is this one. These are part of the renal medulla. So that renal medulla is that dark brown inner region, and it's kind of cone-shaped, composed of that cone-shaped kind of structure that are called the renal pyramids. You see that cone-shaped renal pyramids? Cone-shaped renal pyramids. Just keep that in mind. So you have the renal pyramids, part of the renal medulla. Then you have the renal pelvis, and the renal pelvis has many different, two different structures in it that we're going to talk about, cup-shaped structures. That's the renal pelvis, which is the right thing. Just think of it as right before the urine exit. That's the last part where the urine is going to be traveling before it leaves out of the kidney. So it's part of the hilum, which is this portion, where blood vessels enter into the kidney, and the ureter exits out. That's where pretty much the part of the hilum is. And what we are going to discuss a little more is, like I said, the renal pelvis. This area, this renal pelvis is a funnel kind of shaped, is a cavity that is funnel shaped, and drains the urine into the ureter. That's the main function. But it has two parts. It has the major calyx and has the minor calyx. And like I said, the plural of those is calyces. So you have more than one. That's why we call it calyces. So the minor calyx is the one that you see here, this area at the top portion. The major calyx is closer to out into the renal pelvis, closer to the ureter. And so here we go, renal. And of course you have those called renal columns that you see between the pyramids, renal columns that drive or transport the urine into the renal pelvis area. And of course you have the one and only ureter. And like I said, it's surrounded by fat on the outside that gives it the cushion, but there is also fat within the renal sinus. So these are the main parts of the kidney. And when you sometimes, we do dissections of the kidneys, and these are the main parts that you need to be able to identify if you are to dissect one. Now, within the kidney, you're going to have the main functional unit of the kidney, which is the nephron. And the nephron is nothing but a tube-shaped, just tube kind of structure. And within that tube, you'll have the many different parts, and those parts where you are going to reabsorb, certain ions or certain molecules, and then you're going to excrete others that will later on become urine. So you reabsorb back things into the blood, or you keep them in the tubes that you see here, and eventually, if it gets to that point, it will become urine and is excreted out. We'll talk about the process in a few minutes as well. So that's the main part of the kidney. Proximal convoluted tubule. This one is the first section of the renal tubule, like you know, is located in the cortex, and it's composed of simple cuboidal epithelium. Remember that from chapter 4. Epithelium, and those simple epithelium have a microvilli at the top of the cell membrane. They're cell membranes. That makes sense since you're absorbing and secreting through the microvilli. Then, of course, you have the nephron loop or the loop of Henle. Or the nephron loop. This is the second portion of the renal tubule. It's located in the cortex and the medulla, but remember, if it's just only a tip of it in the cortex is short, that's the cortical one, and if it's long, deep into the medulla is the juxtaglomerular nephron. So you have the cortex, it's in the cortex and the medulla of the kidney. And it consists of descending limb and an ascending limb, like I showed you before. The descending and the ascending portion of it is composed of simple squamous epithelium, and when I say simple squamous epithelium, you know I'm talking about the one layer of flat cells, which means, if you recall from chapter 4, that's where exchange is. That's a capillary system, extensive. That's anytime you have simple squamous epithelium, you know for sure there is exchange taking place. Just keep that in mind. Exchange. And the thick ascending limb, the thick portion of it, there's a thin and thick portion of the ascending limb. The thick portion is composed of simple cuboidal. So the thick portion of the thick part of the ascending part of the loop of Henle is made up of simple cuboidal and some, I need to add this one, and some columnar epithelial cells. So, but keep in, like I said, keep in mind you have the afferent and efferent arteriole that go into the glomerulus. You have the afferent, which goes into the glomerulus. The efferent goes out, leaves the glomerulus. And then, of course, you have the distal convoluted tubule, DCT. This one is the third part. It's located in the cortex of the kidney. It's composed mainly of simple cuboidal epithelial cells. Epithelium, and it is the last part of it, the last part of the collecting ducts. The last part of the DCT, the very last part of it, is composed of cells similar to that of the collecting duct. So that takes me to the collecting duct, which extends from the cortex to the medulla. So that makes sense. This is where the urine is going to finally become urine. The filtrate will, now you're called the filtrate urine. So as soon as the filtrate hits the collecting ducts, you change the name from filtrate to urine. It goes into the medulla of the kidney, and it receives that urine from the distal convoluted tubule, and is composed, this collecting duct, like I said, the last part of the collecting ducts, the last part of the distal convoluted tubule is very similar to the collecting duct. And that last part of the distal convoluted tubule and the collecting duct is cuboidal epithelium. It's simple, actually simple. Cuboidal epithelium, which is made up of some functional cells or specialized cells, and those specialized cells are called the principal cells and the intercalated cells. And of course, like I said, you have the vasa recta that we spoke about. If you recall, I said here is the glomerulus, here is the Bowman capsule, here is the efferent and efferent trioid, here is the proximal convoluted tubule, here's the loop of Henry. So here's the loop of Henry, and then you have the distal convoluted tubule, and then eventually you have the collecting duct. And if you recall, I said the vasa recta is an extensive kind of network that goes around the loop of Henle. So that vasa recta, or is known as the peritubular capillary, known as the vasa recta, there's a lot of exchange that takes place in this area. And just keep that in mind. There's a lot of exchange that happens here, and usually it's deals with the sodium. It's called the countercurrent multiplier system, the countercurrent multiplier system that takes place here, the sodium chloride ions and water. So that's very important to talk about later on. That's the main part of the nephrons that we are talking about here. So let's go back to the desktop. So here is one more structure. You see that you have the structure of the nephron. Here is your glomerulus, the glomerulus. Here is the capsule, the space in between, the Bowman capsule, which is around it. The space in between is where the actual filtrate is going to take place. Here is the efferent arterioid taking blood away. Here is the afferent going to take blood in. Notice how the afferent is thicker than the efferent, and that's a lot to do with blood pressure too. That regulates blood pressure as well. You have the proximal convoluted tubule. So when you say you have hypertension, then this was going to relax. You don't want to have too much pressure going into the glomerulus, it will damage it. So this will relax if your pressure goes up, and if pressure drops, then this will constrict to allow for the pressure to go up. So just keep that in mind with regards to how it responds to hypertension. So you have that, you see the blood supply going around the nephron. Here is the vasa recta, see that? And you have then the venules, the venule system taking the blood out back to the inferior vena cava. So I'm going to make this a little simpler for you. I'm going to go ahead and go back to the whiteboard. So what you have is the glomerulus capsule. I'm going to do that in, let's see, just simplifying it, and I hope I do a good job doing that. Let's see. Just simplifying it for you. Then you have a blood supply, let's put it in red. So here is your afferent, arterioid. Here is your efferent, arterioid. Here is the vasorecta, or let's say the peritubular capillary. Here is your glomerulus capsule. Here is the fluid or the filtrate going through the tube. And you can see here is part 1. Part 1 is the filtration. That's where the glomerulus, the blood plasma, dissolved substances are going to be in the filtration system now, in the filtrate. Of course, the large proteins and all that will remain in the blood, red blood cells and white blood cells and all that will remain in the blood, whereas the rest of the filtrate will be, the rest will be in the filtrate. Then you have the second step, which is you're taking back everything. The second step, that is known as reabsorption. You're reabsorbing everything back into the blood. Reabsorption, that's along the entire tubes, you know, distal renal lobe of Henle and proximal lobe of Henle and distal convoluted tubules. And that's where you collect the water, ions, and the substances that you are going to need back into the blood. And the last step is secretion. That's number 3. Secretion, and that's all along, again, the renal tubules, all along. You're secreting things along the way and you're gaining things, and that will be your waste, your excess ions and all the things you need, the waste, and that eventually will become the urine, which will dump into the collecting duct out through the kidney into the ureter. Okay, I'm going to go back to so again, you have the first one that I spoke about, number 1. Oops. Here is the filtration. Now you have a filtrate, and all along the way, in and out, you are doing number 2 and number 3, which is, oh, that sounded a little bit, so that you are reabsorbing and you're excreting waste constantly throughout all the tubes. So if you want to, let's talk a little more about the actual. Again, here we go with the different parts. Here is the two types of nephrons. Like I said, there is the cortical nephron that is deep into the medulla, but just the top portion of the medulla. We can see the lobe of Henle going just down. So here's the cortex, here is the medulla of the kidney. And then if you take a look at the juxtamedullary nephron, it actually goes deep, the lobe of Henle deep into the medulla. These are the two different type of neurons you'll see. So that one sits high in the cortex, as you can see in this picture, and it's the majority of the nephrons are actually cortical nephrons. But then you have the juxtamedullary nephron, which goes deep into the medulla, and they have very long kind of lobe of Henle, and their main job is to regulate water balance and urine concentration. So just keep that in mind. These are a smaller part of the smaller part of the nephrons, less of them. Now, when you deal with the juxtamedullary apparatus, since we're dealing about water, it regulates the secretion of renin. And if you recall, I said we're going to talk about renin later on this semester. Renin is very important and is very active with aldosterone. So we'll talk about that. The top portion of the ascending limb of the nephron passes, between the afferent and efferent arterioles. We know that one already. And the ascending limb of the lobe of Henle comes in contact with the afferent arteriole to form the juxtaglomerular apparatus. And you can see that also from the picture. So finally, there are two types of specialized cells when it comes to the juxtaglomerular apparatus. There is around they are in that nephron is the first one is called the macula densa, and these are tall cells that are packed in the ascending limb. And you have the juxtaglomerular cells, and these are large, smooth muscle cells that make up what you call the afferent arteriole. So these are two specialized functional cells to keep in mind. Now this is going to get into a little more into the renin. So what I will do is I want to discuss the glomerular filtration for a minute. I don't think that there is a slide here that does that for us. So let me see if I can. Yeah, here we go, glomerular filtration. So the glomerular filtration is a little complex because there is a lot of two different, different types of pressure that influences the filtrate and forces the filtrate to come off into the Bowman capsule, into the space between the glomerulus and the Bowman capsule. So the glomerular filtration, like I said, that's step one, which is the urine formation, and the substances move from the blood in the glomerulus into the glomerular capsule, to the space between, and that water and small dissolved molecules can be filtered. So all the water, some small molecules, ions and all that will be in the filtrate, and the large molecules, like I said before, such as large proteins, let's say albumin is one, and glucose will all remain in the blood as they go, because they can't really pass through. Now the glomerular capillaries are many times more permeable than the other capillaries in the system. They're very permeable, but they have, like I said, space slits that are called fenestrations. And remember, I said on one of the slides, they call these slits fenestrations. And they have the glomerular filtrate now is formed when the blood is forced into the glomerular capillary system. All right, but the way it's forced, it's through pressure. It's a play game with the pressure kind of system. So the filtration pressure. And that's what I want to talk about, that we'll discuss these two slides with you. So I'll go ahead and switch back to the whiteboard again. New slide. So you have the glomerular capsule. You have the blood vessels. Let's see. You have the glomerulus. So here is the afferent. Here is the efferent. So blood goes in. Here's the blood leaving out. Here is the glomerulus, like I said. Here's the Bowman capsule, the space here. Remember, this is also the glomerular capsule. This is the space. So this is the capsule. This is the space actually that makes up. That's the space here. That's where the filtrate is going to be. And here is the proximal convoluted tubule. At this part, here are the cells that make it. All right, so the different pressures that we're going to talk about just to show you how the filter is made. There are three different pressures. The first pressure is called the glomerular blood hydrostatic pressure. I need to charge my computer. Give me a minute. I'm going to stop for a minute. So you have the first type of pressure, which is the glomerular blood hydrostatic pressure. And this is, we call it different depending on the textbook you're reading. So it's anywhere between 55 millimeters of mercury to 60. So I'll just say 55. Millimeters of mercury. That's the first pressure. And that pressure is the type of pressure that, again, that goes into the afferent arteriole. So this is the pressure going in. That's the first pressure that plays a role in forming the filtrate or forcing the filtrate to leave the blood into the Bowman capsule space. The other pressure that we're going to talk about that plays a role too is the capsular hydrostatic pressure. So that is about 15 millimeter of mercury. And so that's one more pressure. And there's another, and that one you'll find here. This pressure you'll find in this space here, the pressure in this area. And then, of course, you have the last pressure, which is number 3, and that's called the blood colloidal osmotic pressure. And this one would be right there between the actual capillaries. This one is abbreviated as the glomerular blood hydrostatic pressure is abbreviated as capital B, capital G, capital B, capital H, capital P. It's easier. The capsular hydrostatic pressure is CHP. And the blood colloidal osmotic pressure is BCOP. So now if you see these different pressures that play a role forces the plasma to form or to be pushed out of the blood into the space, and that will form the filtrate. So the fluid now in the space, because of that pressure, will form the filtrate that will go through the proximal convoluted tubule down through the other loops, where we're going to reabsorb and excrete contents in and out of it, substances in and out of it. Now, since you know the 3 different pressures that I mentioned in regards to the glomerulus, you'll see that the pressure plays an important role. So we have to kind of figure out the net filtration pressure. And that means, so that's N net filtration pressure, NFP. That will equal to all the pressures that we mentioned before. It equals the glomerular blood hydrostatic pressure, glomerular blood hydrostatic pressure, minus the capsular hydrostatic pressure, minus the blood colloidal osmotic pressure, which means that would be 55. Like I said, some books might make it a little more or a little less, but 55 millimeters of hemoglobin. Oops, switch that around. Minus the 15 millimeters of hemoglobin. I'm sorry, of mercury, HB. I keep saying hemoglobin for mercury, I apologize. And the 30 millimeters of mercury. That will give you a total net of 10 millimeters of mercury as the net pressure. And this net force pressure drives the fluid flow from the glomerular capsule or capillaries of the capillaries into the glomerular capsule, to the renal tubule, PCT, lobe of Henle, and the DCT. Now, the rate at which the fluid is filtered in the renal corpuscle is called the glomerular filtration rate. So the glomerular filtration rate is the rate by which the fluid is filtered in the renal corpuscle. And it is about 105 milliliters per minute. Remember, that's in the capsule. 105 milliliters per minute for females. And 105, but for males is around 125 mLs per minute for males. So, like I said before, reabsorption of substances from the filtrate depends on the concentration and the rate of the flow. So if the glomerular filtration rate is too high, then substances are not going to be reabsorbed adequately and leave the body in the urine. And because it's difficult to collect material that's flowing too fast. But if the glomerular filtration is low, then you get to reabsorb more and release more waste because now we have enough time to do it. So you have an adequate kind of excretion taking place because the time allows for it. So again, when it's too fast, you're not absorbing and secreting as much. When it's slow, you're absorbing and secreting more. And remember that the afferent arteriole when it's being more restricted than the efferent. This way when you are exercising or moving, all right? And so now you can easily follow the steps and see why it stays there, why it's you get more filtration or not if you're exercising or relaxing. Now, because the filtration membrane normally prevents the passage of large size protein or bigger like such albumin, the filtration, if there is any damage to the glomerulus, then those proteins will make it into the filtrate. And that when you do a blood test and they find out that you have high albumin or glucose, or I'm sorry, high proteins, that says that you have some kind of kidney disorder or a problem. You might have an injury to the kidney, a disease, some kind of disease. You might, believe it or not, high blood pressure. So that's something to keep in mind. So one of the things that they look into the GFR to check it is to ensure that the filtrate that goes into the glomerulus, the glomerular capsule, that goes into the glomerular capsule out, so that filtrate does not include lots of protein, large size proteins. If it does, that means there is damage to the glomerulus. And the number one problem, believe it or not, that causes my kidney damage is blood pressure, is hypertension. So chronic hypertension is a serious, serious problem. And we're going to talk about blood pressure also almost in every chapter from this point on. All right, let's go back to the PowerPoints. Make sure that we have it all. So that's what the slide is, kind of covering everything that I told you before that I wrote on the slide. That's what these slides are. So again, the GFR, as you can see, the regulation of it remains constant throughout the filtration process because it's auto-regulated. There are certain conditions that override it. For example, if you have an increase in body fluids, the mechanism responsible for regulating it is, number one, is the auto-regulation, and that's coming up later on as well. You have the increased, that's due to the increase of sympathetic impulses that keep the GFR constant and maintained through changes of blood pressure. And that is, the blood pressure is also affects the afferent and efferent arterioles as they constrict or dilate depending on blood pressure. There is also a hormone called the renin-angiotensin system that we'll talk about later on as well. That's the liver and the renin that is being released, the angiotensin from the liver and all that, that works with aldosterone to affect sodium absorption and excretion, which again, sodium will affect the blood pressure volume, blood volume. Aldosterone and allows you to retain sodium, which eventually retain water, increase the blood pressure, whereas by increasing blood volume, whereas you have the atrial natriuretic peptide, again from the heart, that secreted by the heart. What that does, or the ventricular natriuretic peptide, either one released by the heart, does the opposite, allow you to excrete sodium into the urine and release it out. Therefore, when you let go of sodium, you let go of water, blood volume drops, blood pressure drops. So these are kind of different regulatory processes. Here is the renin-angiotensin system. With the renin-angiotensin, you have the liver. That's very important to keep in mind. Now you have the liver, you have angiotensinogen being produced. The kidney releases renin. Together form what you call the angiotensin 1. That angiotensin 1, you have an enzyme called angiotensin converting enzyme, ACE, converts angiotensin 1 to angiotensin 2. Now, once angiotensin 2 is made, it has many options, has many effects. One of them vasoconstriction of blood vessels. It interacts with the adrenal gland to release aldosterone, and all, which again, aldosterone, you retain more potassium, more sodium, and blood pressure begin to pick up, or it increases ADH secretion, and by doing so, that means you're going to retain more water and blood pressure begins to pick up again. And of course, stimulate thirst, so you can drink in order for you to increase water and bring blood pressure back up. So you have, this is what they call the renin-angiotensin system, that enhances or works what you call synergistically with aldosterone to allow to increase the blood pressure and with the ADH. So again, the renin-angiotensin system obviously responds to hypertension, to drop in blood pressure. When that happens, you'll have the liver releases angiotensin, the kidney secretes renin, together make the angiotensin 1, and the presence of the angiotensin converting enzyme changes into angiotensin 2, which means that it's going to cause blood vasoconstriction, is going to allow the anterior pituitary gland to release antidiuretic hormone, arouse the adrenal gland to release aldosterone, which again, that influences the amount of sodium being absorbed or the water being absorbed or into the blood, which forming, increasing blood volume, which means increased blood pressure. Increased blood pressure. So now we are going to go into a little more information about the actual absorption and secretion of the kidney was through the proximal convoluted tubule, the lobe of Henle, and the distal convoluted tubule. So tubular reabsorption, as you can, I'll explain it in more details in a few minutes as well. The tubular reabsorption, you have movement of substances from the renal tubule into the interstitial fluid, which is the space between the nephron and the blood vessels, and the diffuse, and then into the capillary system. So it goes out from the nephron, out into the interstitial fluid, that's the white space, and then into the blood vessel. That's reabsorption. You're reabsorbing molecules, and most of the tubular reabsorption occurs, 70% of it occurs in the proximal convoluted tubule, and like I said, it's actually lined with microvilli to allow for that. They have tubular secretions within the movement of waste from the peritubular capillary, into the interstitial fluid, into the nephron, into the renal tubule. So our different parts of the renal tube reabsorb specific substances. So and it's transported back and forth. And the main one that that will allow for the transport of molecules from the blood vessels into the nephron, from the nephron back into the blood vessel, is active transport. And active transport requires energy, like I said. Active transport means you're going against the concentration gradient, which means it's going to require ATP, and you're going against the concentration gradient, meaning going from an area of high concentration and from an area of low concentration to an area of high. You're going against the gradient, and this is limited capacity because you have there are proteins that do it, and there are a number of them you have. It's not like you have them everywhere. There's a certain number of them that will do the job, and this is highly active. The renal plasma, if the renal plasma threshold is reached, that means it will only take what it can, and the rest will remain into the urine. An example of that will be the glucose. So if you are diabetic, and I'm sure you probably know someone, you have enough of those proteins, you have a number of those proteins that reabsorb the glucose back into the blood. So let's say here is the renal tubule, and here is the blood vessel at the very top. Here is the blood vessel. Then in order for you to have enough protein channels, so I have enough protein channels here. that if the glucose were going through, it will take it and push it back into the blood. So if there is a few of them, or enough up to the threshold or below, all of those glucose molecules will be put back into the blood, and therefore there is no glucose in the urine by the time you're done. Now, if you are diabetic, there's too much glucose that is above the threshold. So even though they're working really hard taking the glucose back into the blood, the extra glucose that you have is going to keep going through the filtrate away from the proximal the tubule all the way to the collecting duct, which will become urine later on. And then when you test for the glucose, you'll see that you have glucose in the urine, and that's a sign that you have, and that's pretty much that tells us that you have diabetes. So again, these are numbered. The active transport proteins are numbered. There is a specific number of them. And whenever you have too much of a certain substance, then they're unable to put it all back into the blood, and the excess will end up in the collecting duct, in forming the urine. And that's one of the reasons why we check for glucose. And if you have proteins in your urine, that's also, I said, that's also a problem, which means that it's unable to send the proteins back into the blood, and the large proteins are not supposed to make it into the filtrate anyway. So there are large proteins like albumin that tells us that the glomerulus itself, there is a certain damage there, since it did not prevent the proteins from remaining into the blood, and there was enough damage where it actually leaked out from the blood into the filtrate. So that's one. Active transport plays a role in the tubular reabsorption. Osmosis is another one. So water is reabsorbed from an area of high concentration to an area of low concentration, depending on where the ions are. And we spoke about how water moves where the sodium is and all the different hormones that play a role with that. And you have the endocytosis. And the endocytosis is the movement of molecules or proteins as they absorbed into the cells. If you recall that from chapter 3 last semester, endocytosis is just it's a cell that extends its cell membrane out, and then it takes in a molecule in by extending its plasma around it and absorbing it in. And that's how the cells, there's the white blood cells, phagocytosis, if you remember, part of it, that takes in a large molecule and use it. All right, now let's get into the actual absorption and reabsorption of different molecules. The first thing we're going to talk about is the proximal convoluted tubule. I'm going to go back to the as you can tell from the whiteboard, it is easier to makes these slides easier to understand as you go through them. So again, you'll have keep in mind the actual structure of the nephron. Let me just put it right on the side. So here is the glomerulus, all the different structures. Here is the proximal convoluted tubule. Here is the lobe of Henle. Is the distal. And then you have the collecting ducts. So let's start with the proximal convoluted tubule. Take this part. So the proximal convoluted tubule, it deals a lot with sodium and potassium, water are absorbed equally. And that means that the osmolarity of the filtrate will remain the same. The osmolarity of the filtrate will remain the same. And here you also have hydrogen ions, ammonia, let's see, ammonia, H4, and urea. There's one more, I think of it. Creatinine. These are secreted in the proximal convoluted tubule. So what you have, these are all secreted. So what you have, sodium, potassium, water absorbed equally to allow for constant osmolarity, but you also secrete the hydrogen ions, ammonia, urea, and creatinine. Now, the loop of Henle, this portion here, so there's the first one, the PCT. Now, for the loop of Henle, you have absorption of loop of Henle. This is loop of Henle. This is you have the absorption of water, sodium, potassium. In fact, these sodium and potassium are, the water and sodium potassium are separated, different absorption depending on where in the nephron takes place. So what you have is that water is absorbed. Just keep that in mind, that water is absorbed water is absorbed in the descending limb of the loop of Henle. So it's this part. And the sodium and potassium are absorbed in the ascending link. Limb of the loop of Henle. And that difference between absorption of water and sodium and potassium along the, remember this vasa recta that supports all that system here between it and the vasa recta. This keeps a system that's called the countercurrent multiplier. The countercurrent multiplier, which means it sets up an osmotic gradient within the medulla. Remember, this part is all in the medulla, the nephron. This portion here is all in the medulla. So that means it's going to set up a concentration gradient in the medulla. And that concentration gradient between water and salt will allow the water to be absorbed and the sodium to be absorbed back into the blood or secreted. So when the filtrate leaves the nephron loop, it's actually hypotonic compared to the blood. So when it gets all the way to this point here, it's about to leave. It goes out from the medulla, from the ascending limb all the way to the medulla. Once it hits the medulla part into the distal convoluted tubule, the blood is actually very hypotonic in this area. Hypotonic. And of course, this will eventually become the urea later on. Now, in the distal convoluted tubule, this portion here, the last part, the distal convoluted tubule, you'll have sodium, chloride ions, and water is also absorbed. Sodium, chloride ions, water, these are absorbed. Calcium is absorbed as well, Ca, calcium. And that's where you have the parathyroid hormone plays a role as well in the distal convoluted tubule. Now again, when you see sodium being absorbed, that aldosterone and all that hormones that interact, that force that reabsorption. But when it comes of sodium, but whereas for the for the calcium, they know the parathyroid hormone is going to play a role too. And finally, when you get to the late part of the distal convoluted tubule and the beginning of the collecting ducts, you'll have the cells that I told you about, the principal cells and the intercalated cells. Those cells that I mentioned before, the principal cells absorb sodium and potassium, and that's influenced by aldosterone. So aldosterone is going to play a big role here, aldosterone. And the intercalated discs help reabsorb potassium and carbonate ion and secrete the hydrogen ions out. So the intercalated discs will allow for the blood to become more alkaline. So the intercalated disc reabsorb the potassium, reabsorb bicarbonate ion, HCO3. Like I told you before, that if you have more of that, then it becomes more alkaline and secretes the hydrogen ion. When you secrete the hydrogen ions, it remains in the collecting ducts. Then obviously the blood, since you have less hydrogen ions, it becomes less acidic. And so the permeability of the cells to the water are regulated by the antidiuretic hormone, and then the antidiuretic hormone plays a role in this area as well. So that antidiuretic hormone allows for us to retain the water back into the blood, so you absorb the water. And in the absence of antidiuretic hormone, then you are going to lose the water and you're going to have more urine. So the more ADH, the more water you absorb, the more concentrated the urine is and less fluid you release. The less ADH you produce, the more water you're going to secrete, so the more diluted the urine will be. So if you're hydrated, your urine will be somewhat less yellowish or more toward less yellow kind of color. And if that's if you're hydrated. But if you're dehydrated, then the urine will be dark yellow, tilting toward the little orange, but very dark yellow and very concentrated with less water coming out, or less urine, releasing less of the urine. All right, so we got that out of the way. Let's go back to the slides. So these are the slides that kind of cover the summary that I just gave you. Again, so here you can see the ADH. Even though we talk about ADH regulating the concentration of volume, make sure you go through that, because I discussed it a few minutes ago. And here's the counter current multiplier. That's the one you see where the vasorecta is, and the different types of concentrations along the ascending and descending loop of Henle. So you have the countercurrent mechanism in the nephron loops that ensures that the tissue in the medulla becomes more hypertonic, and so that will allow the urine to be concentrated. So the urine at the end of the loop of Henle. So if you take a look at the urine is most concentrated. So here is the loop of Henle. Here's the descending. Here is the ascending. And this area here, the very bottom, this is where the urine is more concentrated, very highly concentrated. The vasorecta, the blood supply that goes around it, like I mentioned before, this is for the juxtamedullary nephron, contribute to that kind of countercurrent mechanism. So the things to remember is that the thick ascending limb of the nephron loop is impermeable to water, but actively absorbs the sodium and chloride ions. The thin descending loop of the nephron is permeable to water, but not the solute, not the sodium and potassium and all that, those ions. So that tells you right there, if you take a look at the thick ascending and the thin descending, that the thick ascending is impermeable to water. So no water go in and out. There's no change of water, no absorption of water, but there is absorption of sodium and chloride ions. Whereas with the descending is the opposite. It's permeable to water, which allows the reabsorption of water or the secretion of water, whereas it does not allow that for the solutes. So since the thin descending is surrounded by, so now since the, and so be careful with these words, since the descending limb of the loop of Henle is surrounded by a hypertonic fluid, remember the descending is permeable to water. So hypertonic fluid, water leaves by osmosis, and the fluid inside becomes more hypertonic. So that should kind of make sense to you now. Whereas the concentrated fluid moves into the descending limb, or into the ascending limb. So the concentrated fluid will move into the ascending limb, where sodium chloride is actively reabsorbed. So this process keeps repeating. The NaCl concentration in the ascending limb increases or multiplies. That's where the word multiplier comes from. So the concentration of the fluid on both the tubular and the interstitial fluid within the medulla increases toward the deeper portion of the renal medulla. So as you go down the renal medulla, the concentration of the fluid will begin to increase. But remember, talking about the interstitial fluid, the fluid, the tissue between the actual nephron and the blood vessel, the tissue in between. And here you see it again. Here is the isotonic fluid going through the nephron. Here is water leaving out of the nephron. It is permeable to water. And then on the other side, the thick ascending is impermeable to water. So now, but it is permeable to solutes. So now the solutes are leaving into the interstitial fluid. And that's what causes the vasa recta is all around that. So that's what causes the counterrecurrent multiplication, because as you go up, it becomes more and more concentrated. There's a counterrecurrent, see that more sodium is being released. So here is a good the counterrecurrent multiplier. Here's a step 1, 2, and 3, kind of show you how things go. So 1, you have water, sodium release that is very salty. Now as you have more and more water being released, more and more water here, this will be far more salty. And this eventually will be the very, very salty, and the urine here is very highly concentrated. Here's another picture showing you the vasa recta around the tubule, and just apply what we mentioned here, those 3 parts. Just make sure you follow those. If you forget, follow those steps. Oops. Follow those steps. The thick, you follow these steps, one step at a time, from the thick and the thin, and which one is permeable, which one is impermeable, which one have more, where osmosis is taking place. So follow those steps, step by one. So these steps as you look at this slide. So I advise that you kind of print out this slide or something in your notes. Make sure you write that down in your notes, and then you compare your notes to what you see in this slide. So it can make more sense to you. So here is the function of the nephron part, different parts of the nephron. You'll have the renal corpuscle, which is made up of the glomerulus and the glomerulus capsule. In the glomerulus, you have filtrations of water and dissolved substances from the plasma. The glomerulus capsule now will have the filtrate that will be shipped or sent into the proximal convoluted tubule. That's where you have reabsorption of glucose, amino acids, creatinine, lactic acid, citric, uric, ascorbic acid, phosphate, sulfate, calcium, potassium, sodium, and all of that is via active transport. But you absorb what you want and you excrete the excess, keep that in mind. So you reabsorb the proteins by endocytosis, and you absorb the water by osmosis. So there's 3 different methods: the active transport for ions, the endocytosis for proteins, and osmosis for water. And of course, you have reabsorption of chloride ions and other negative ions by electrochemical attraction, so that you can say charge. So that actually makes a lot of sense, since you have, if sodium goes in one direction, then obviously it's plus, the chloride ions will follow it, is negative. So it's the charge attraction. Again, so you'll see that there are many ways that the proximal convoluted tubules is going to reabsorb or secrete molecules in and out from the nephron to the blood, and from the blood vessels back into the nephron. And that's one by active transport, another by endocytosis. In case of water is osmosis, and charge for some ions. Now, there is also active secretions of substances like penicillin, histamine, creatinine, and hydrogen ions that are going on as well. Then you have the descending loop of Henle, this one where you reabsorb water back by osmosis. You have the ascending limb of Henle, that's where you reabsorb sodium chloride ions, potassium ions to active transport. And then you have the distal convoluted tubules where you reabsorb sodium again by active transport. See how important it is for sodium. And then, of course, you take the water back by osmosis, and you excrete or secrete the hydrogen ions by active transport. You know, that's plus affecting the pH of the plasma later on. And of course, you have the secretion of potassium by charge, by electrochemical attraction. Finally, whatever is left, you have will be in the collecting duct, and the collecting ducts, you absorb the water back through osmosis, and the rest will become urine. And that sounds easy now that you covered all that. So here's the different parts that you secrete. You have the urea, which is a byproduct of the amino acid catabolism. The plasma concentration will reflect the amount of proteins in diet. So what you have, it enters the renal tubule through the glomerular filtration. Glomerular filtration. It undergoes both the tubular reabsorption and tubular secretion, and 80% is reabsorbed and 20% of the urea is secreted in the urine. Then you have uric acid, which is a product of the nucleic acid metabolism. It enters into the renal tubules through glomerular filtration. Active transport is the main mechanism by which you absorb it. 10% of the uric acid enters in the urine through the tubular secretion, 10%, and this is excreted. The urine composition, composition reflects the volume of water, of course, and the solids that you have in that urine. The composition is 95% water. But again, it varies because due to the diet that you have and the physical activity that that plays a role too. So you have 95% of water that makes up the urine. You have many metabolic wastes such as urea, uric acid, creatinine, and it contains trace amounts of amino acids and some other electrolytes. The urine volume is anywhere between 0.5 to 2.5 liters per day. You have about 50 mLs to 60 mLs of urine output per hour if you're normal. And the volume varies depending on the fluid that you take and the environment, what you're doing during the day. And of course, these are the slides you can go through and read more about it. Now, how is the storage and elimination of urine? If you want to look back into the actual big picture, you'll have the nephron and the collecting duct. You have urine formation. Should have turned my phone off. So you have the nephron and collecting duct that cause the urine formation. That urine goes through the renal papilla into the minor calyces, into the major calyces, through the renal pelvis, into the ureter or the urinary bladder for storage, temporary storage, then urethra, which carries it out of the body. So again, if you go through that with the kidney, you go from the renal papilla into the minor calyces, major calyces, into the renal pelvis, into the ureter, urinary bladder, and then out in the urethra. So the ureter is a tube organ that is about 25 centimeters long. It begins at the renal pelvis in the kidney and ends at the urinary bladder in the pelvic cavity. It has 3 layers. It has the inner mucus coat, or it's made of transitional epithelium. And notice the transitional, if you recall, are elastic, so they allow for expansion. The middle muscular coat, and then you have the outer fibrous coat of it. Then you have the peristaltic waves that transport the urine from down to the urine along the ureter to the urinary bladder. Now, if it's obstructed by a kidney stone, for example, renal calculus, and that will trigger a uterorenal reflux, and strong peristaltic waves in the obstructed uterus can move the stone toward the urinary bladder. But I can tell you it's extremely painful, and that will cause reduced urine that being produced by the kidney. So here is the 3 different layers of the ureter. Here's the mucus coat. Then you have the lumen. So the mucus coat, you have the space, which is the lumen. You have the muscular coat, is the smooth muscles. And then you have the fibrous coat on the outside. And then, of course, you have adipose tissue, fat. And you can read about the kidney stones and all that. Now let's talk about a little more about the urinary bladder. Notice that the urinary bladder is a hollow, distensible muscular organ that is located in the pelvic cavity. It is posterior to the pubic symphysis and inferior to the parietal peritoneum. And that's where the urine is stored. It contacts the anterior wall of the uterus. It contacts the anterior wall of the uterus and the vagina in the females, and it lies posterior against the rectum for the males. There is the triangular or trigon at the floor of the bladder that has opening for in its 3 corners, 2 to the ureters and 1 to the urethra. The walls consist of 4 layers. Yeah, and we'll talk about that too. You have the inner mucus coat, which is made of transitional epithelium to allow for the bladder to expand. You have the submucous coat, you have the muscular coat, the smooth muscles, and you have the outer serous coat, which is the surface area. Now, the smooth muscle fiber of the muscle coat comprises of the detrusor muscle that I will show you in a minute, and then you have the internal urethral sphincter, which surrounds the neck of the bladder. And that's the sphincter, is like the valve that will open to allow for the urine to leave the bladder. So here is again the different structure between male and female. Notice how the urinary bladder here is for the female, whereas the location of it for the male. So here's the urinary bladder again. Notice that the urinary bladder is made up of many parts. So I will go back into you can look at that picture printed as I'm lecturing, or look at the similar picture in the textbook. So here is the urinary bladder. First of all, here's the layer on the outside. This layer on the very outside is the peritoneum. Right here is the bladder, the actual bladder. So this is the layer of the bladder. Here is urethral openings. course, from here, you have the ureter. The inside of the bladder, the lumen, is made up of mucosa that we call the rugae, which is the mucosa of the urinary bladder, or the anterior, what you call the uh, the lining of the bladder, which is made of transitional epithelium. And then, of course, you have the internal right there, this space here. This is the internal urethral sphincter. Urethral sphincter. This one is smooth muscles that opens and closes the urethra, and it is involuntary. Then you have the external urethral sphincter. That one is a skeletal muscle, and it opens and closes, but this one is voluntary. So remember, this is a skeletal muscle that's voluntarily controlled. And of course, from this point on, you'll have the external urethral orifice. Which is opens to the outside, the urine to the outside. This is, of course, the urethra. The muscle here that makes up the actual bladder is the detrusor muscle. And this consists of 3 layers with smooth muscles that can stretch and fill up the bladder with urine. So that's really the most, all the different parts of the actual urethra. Let's see if these are the same parts you see on the slides. So here we go. Like I said, here is the detrusor muscle, which is made of smooth muscles, like I said. Here is the lining that make up the muscles. Here is the lining is transitional epithelium. Here is the mucus coat. Here is this detrusor muscle. Here is the trigone. These 2 openings that looks like a triangle like this. And here is the sphincter. There's the internal urethral sphincter that is involuntary. And here is the external sphincter. So then you have the urethra. The urethra then is a tubular kind of organ that sends the urine out from the bladder. It lines the mucous membrane. It's lined up with the mucous membrane, and it's longitudinal, kind of a smooth muscle. It has mucous glands that are called the urethral glands. In the females, about 4 centimeters long, and the external urethral orifice is separate from the vaginal opening. So they're separate. Whereas for us males, you have 19.5 centimeters long. It has dual function. It's for both urination and transport of the sperm. They have it has 3 secretions. You have that go into it. You have the prostate gland secretions. You have the membranous secretion of urethra, and you have what you call the spongy urethra, which terminates at the external of the urethral orifice of the penis. So three sections. You have the prostate part, the prostatic part. You have the membranous part, and you have the spongy part. 3 different parts. The prostate is there. It's where the prostate gland is. This again goes through the different type of urethra in male versus female. And now we're going to talk about micturition, which is the urinary reflex and how you release urine. So if you go back, the first thing you'll notice that number one, when it comes to micturition, is that the bladder has to fill. So I'm going to use it in different color. So the first thing is when the bladder gets, when urine is step one, when urine is about 200 to 400, some books might have 500, but 400 mLs will cause the urine to begin to fill up, put pressure on the actual lining of the bladder, and that will force it to stretch. Now that stretching causes the receptor. That's one, is you fill it up with about 400 mLs. It can actually take up 1 whole liter, by the way, but let's say 400 mLs. It stretch, and we begin to stretch those receptors. Stretch receptors send an impulse to the spinal cord. Send an impulse to the spinal cord. That will activate the parasympathetic nerve activity. Parasympathetic activity, which causes the contraction of the uterus muscle. Contraction of the uterus muscle, and causes the relaxation of the internal sphincter. So this one contracts, and this one relaxes, and now the urine begins to flow out. And then the spinal cord, of course, the spinal cord inhibits the motor neurons that causes the external. So now the external urethral sphincter is controlled, is voluntary. So if you don't want to urinate at the moment, you can control it, but the urine will be here, you can control it. Now, if it's for some time. And so the spinal cord can inhibit that and keep this closed till you're ready to do it. So that the spinal cord now sends a message. Now you can, messaging between the spinal cord and the external urethral sphincter. If you're ready, you release and you urinate. If not, it will remain in there. So the last step would be the urination. So if you release, then obviously you're urinating. Urination or micturition. And finally, the nerve impulse from the cerebral cortex, can control, like I said, from if the cerebral cortex send an impulse that is okay, then you go ahead and release, voluntary release, and you're urinating. If not, you can control it for a limited time. So you have the steps that mentioned here that are in a summary with the PowerPoints. So again, here is the urinary bladder distend. Distend means it's going to fill up. So 400 mLs will be enough to start it. The stretch receptors in the bladder will be stimulated, and they send a signal to the sacral spinal cord. Then the parasympathetic nerve, like I said, will send impulses to the detrusor muscle and will allow it to contract, and at the same time the internal sphincter will allow it to relax. So that gives the need to urinate. So the voluntary contraction, now it all depends on the external urethral sphincter. So it can either inhibit the micturition, which means that you're going to keep it for temporary for a while, And that impulse comes from brainstem, the cerebral cortex, or if you want to urinate, therefore the signal is sent to the external urethral sphincter to relax, and that impulse comes from the pons and the hypothalamus, which then you are able to urinate. The micturition reflex. The uterus, the detrusor muscle will contract, the internal urethral sphincter will relax, and the urine is expelled out of the urethra. And so the urinary bladder can hold up to 600 mLs, even though I've seen in the hospital one time someone with 800 mLs of urine in the bladder. I could not believe it when I've seen the number. So it can hold a lot more than 600. And of course, these are finally the last, which is what happens to you as we age. Obviously, the kidney appears to be scarred, grainy, because of the connective tissue accumulation over time. Kidney cells also begin to die over time. By the age of 80, the kidneys have lost about 1/3 of their mass. The kidney shrinkage is because you lose glomeruli, and you get a decrease, obviously, of the GFR by the time you hit 75. You can begin to lose proteins, proteinuria, which is kind of, you remember in the glomerulus, you're supposed to gain that back or not prevent it from going into the filtrate at step one of the filtration. So if you have damage to the glomeruli, obviously you're going to begin to lose proteins. The tubules thicken, they're not as elastic, and you remember they're made up of cells that allow for exchange, and so with thickens you get less exchange, and that will affect the reabsorption of nutrients and ions, so again becomes less efficient. So now it's harder for you to clean and filter your blood. The blood flow slows down over time to your kidneys. The elasticity of the bladder, the ureter, and the urethra also declines over time, and the bladder, of course, will begin to hold less urine. The kidneys are less or not as good as activating vitamin D, and of course, the loss of the bladder or the control of the bladder will lead to incontinence, and you can see that a lot with the elderly. And that covers the chapter. Feel free to email or call me if you have any questions. Thank you.